Hello my dear students, welcome to my YouTube channel. Myself Dr. Sohail Rasool Lone. I am a PhD in Chemical Engineering from the Indian Institute of Technology Roorkee. So if you are new here on my YouTube channel, please consider subscribing, as I will be uploading such video lectures in the months and weeks ahead. So today I will be just giving a brief lecture regarding the basic modes of heat transfer. So I will be starting with the heat transfer. So first we will be discussing the basic modes of the heat transfer. So I'll be actually sharing the screen here, just my presentation. So I'll be doing the screen sharing. So you'll bear with me. Alright, so what is heat transfer? First we need to define what is heat transfer. So heat transfer, as the term suggests, it's a transfer of the heat. Literally we can say it's a transfer of the heat. So we can define it as the energy in transit due to a temperature difference. So for any heat transfer to take place, there should always be a temperature difference. That's a temperature gradient should always be there. Now we need to see what is the difference between thermodynamics and heat transfer. So energy in transit due to a temperature difference, it's heat transfer. So thermodynamics tells us basically how much heat is transferred, that's delta Q, and it also tells us how much work is done on a system, and it gives a final state of the system. So these things are basically governed or dictated by the thermodynamics of a system. Now heat transfer says that with what modes heat can be transferred, what will be the mode of the heat transfer. So it will also give us the rate at which the heat is transferred, that's the rate of heat transfer, and it will also give a temperature distribution inside the body. So heat transfer and thermodynamics, in a sense, they are complementary to each other. Now there are several modes of heat transfer basically. So conduction, convection, and radiation, they are three modes of the heat transfer broadly. So conduction is such a mode of heat transfer, it needs matter. So it can take place for example, in a solid body, you have got the material is composed of different molecules, atoms, or electrons. So when it's heated, so the electrons inside it, they get excited, so they get an energy, and mostly it's because of the kinetic energy. So they get excited and they will start colliding with each other, and this collision leads to the transfer of the heat. So due to the intermolecular diffusion, so this process takes place, there's conduction. So it is not, so it needs matter. Molecular diffusion is a molecule family that takes place at the level of molecules, and it does not need any matter. It does not need a bulk motion of the matter, so it can be a body at a complete static rest. The second mode of heat transfer is convection. So convection is heat carried away by bulk motion of the fluid. So you need a fluid motion, the heat transmitted due to bulk motion inside the fluid, and it needs fluid matter. Convection needs fluid matter. And then we have radiation. So radiation does not need any matter. It can take place, it again takes place due to the transmission of energy by the electromagnetic waves. And then there are several applications of the heat transfer. Heat transfer has application energy production, conversion, steam power plants, solar energy conversion, has several applications. Now heat transfer is mostly used in the chemical process industries for the application of the heat transfer applications, such as use of heat exchangers and the design of the heat exchangers, how we can design the heat exchanger for different heat transfer applications. So there are several applications across industries. So now if we talk about the conduction, so conduction we just now saw that conduction needs matter, and it needs a temperature gradient, it needs medium basically. So if you have, for example, a stationary solid body where we have T1 and T2 temperatures, they are maintained at two different points, and T1 is greater than T2, this is a solid or a stationary or a solid or a fluid body. So this is the heat actually that is transferring. So rate of heat transfer is Q watt joule per second heat flow per unit time. So we can see here, if we want to write a rate equation, how this heat is transferring from one point to another. So just we have a solid body temperatures T1 and T2, this is the heat, Q is, and this K is the thermal conductivity of the materials. Thermal conductivity we will discuss later also in more detail. Thermal conductivity is basically is a characteristic fundamental property of a material. So every material has a different thermal conductivity. So the higher the thermal conductivity, the higher will the heat transfer through that material. So X is the heat flow path. This is actually how much this heat has to actually flow. So heat flow path, we can say it. So A is the area of the heat transfer, and T1 and T2 are two different temperatures. So if we want to write a rate equation in one dimensions, so differential form, we call it as the Fourier's law of heat conduction. So Fourier's law of heat conduction says if you have a solid body with two different ends are maintained at two different temperatures, let's suppose T1 and T2, the heat transfer rate is directly proportional to the area of the heat transfer, that's A, and it is inversely proportional to the heat flow path. So the higher the heat flow path, the lower the heat transfer. So we can write Q equal to minus Ka dt by dx. Now why we have this minus sign here is because this dt by dx will have a negative value. So in order to make this overall term positive Q, so we have to put this negative sign. That's the negative sign indicates the direction, heat transfer in the direction of the decreasing temperature. So K I already said the thermal conductivity, which is watt per meter per Kelvin. A is cross-sectional area, meter square, T is temperature, and X is the heat flow path, meter. So in difference form, if you want to write the same equation in difference form, it will be Q equal to Ka T1 minus T2 X1 minus X2. Or if you write, this was heat transfer rate, now if you write heat flux can be defined as a heat flow per unit area. So it will be just minus K dt by dx, that watt per meter square. Now this is actually a problem. If you can look at this problem, so you have a wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of this. So measurements made steady state operation T1 and T2 are given at the inner and outer surfaces. What is the rate of heat loss through a wall which is 0.5 meter by 3 meter on a side? So you have to actually find the rate of heat transfer through a wall which is this by this, that's this area is this. So it's a very, you have to just use the what's called as Fourier's law of heat conduction. That law you have to use here, and you can actually apply this law, and you can actually find out the rate of heat loss. So now we have actually convection. So in case of the convection, as I already said, convection needs the bulk motion of the fluid matter, and energy is transferred by two means here, by diffusion and by bulk motion of the fluid. So it's the moving fluid. Actually you have two temperatures, T infinity and Ts. T infinity is the outer temperature, you can say this is actually Ts, the surface temperature here. So Ts is greater than T infinity, and this Q double prime is the heat flux, heat flow per unit area. So if we want to write a rate equation, in this case you have, for convection you have, like, this is the flow of the fluid here with the velocity u, and this is we want to write a heat transfer rate Q equal to HATS minus T infinity. That's what heat flux will be Q double prime H Ts minus T infinity watt per. So this H is defined as the heat transfer coefficient. So in the case of thermal conduction, you have a thermal conductivity, is a thermodynamic property, is a characteristic property of basically a material. So heat flux Q is H into Ts minus T infinity. So H is heat transfer coefficient, its unit is watt per meter square per Kelvin. So it's not a property, it depends. So this heat transfer coefficient is not a characteristic property of a matter. It actually depends on the geometry of the particular heat transfer surface. It depends on the nature of the fluid. The nature of the fluid is a laminar flow, is a turbulent flow, or another comes. And it also depends on thermodynamic properties. So there are basically two different types of convection. So convection can either be forced convection, or it can be a natural or free convection. Forced or natural convection, it's induced by buoyancy force. So you apply some external force, like you use a fan or blower. Because of that, you actually try to make some convection inside the system. So another is free convection. Free convection is natural. It happens by its own due to the density difference actually. So it may occur with phase change. There may also be some phase change. For example, boiling and condensation, there is a phase change. So typical values of H, you can have these values of H will be there. So for free convection, you can have these values. For forced convection, you can have higher values, and for boiling and condensation, you can have these values. And similarly, you have a third mode of heat transfer, basically, that is radiation. So in the case of radiation, you do not need no medium is necessary. It can take place by the means of electrons. Energy can take place by the means of electromagnetic waves. So you have different temperature T1 and T2. So rate is heat transfer rate, heat flow per unit time, and this is flux. So radiation equation, you can write heat transfer by electromagnetic waves or photons. So no medium is required here. So emissive power of a surface, for example, some surface emitting some energy in the form of electromagnetic waves, and is released per unit area. It can be simply given by the Boltzmann's law. So it's Stephen Boltzmann. E is equal to sigma, this epsilon. So E is given by epsilon sigma Ts raised to power 4 is what? So epsilon emissivity is the property of the material that actually emits the energy, and sigma is Stephen Boltzmann constant. You can also find its values in the literature. So you can have rate equations. For example, you have a surface and it's maintained at temperature Ts, area is called A, Q radiation and Q convective. So and it's T of the temperature of the surface. So radiation exchange between a large surface and surrounding. Ts is basically temperature of surrounding. Sorry, this T surface. Q of radiation is epsilon sigma Ts raised to power 4 minus T surface raised to power 4. It's watt per meter square. So again, you have a problem here. An uninsulated steam pipe passes through a room in which air and walls are at 25 degrees Celsius. The outside diameter of pipe is 70 mm and its surface temperature and emissivity are 200 degrees Celsius and 0.8. If the coefficient associated with free convection heat transfer from the surface to the air is this, what is the rate of heat loss from the pipe per unit length of the pipe? So you can work out this problem. So I think for today this is sufficient. So I will these were just basic modes of the heat transfer, that's conduction, convection, or radiation. So in the next lecture we will try to see this conduction heat transfer in a more detail. We will see different geometries through which this conduction heat transfer will take place, and we will try to find out the we'll try to derive some correlations how we can get the heat transfer rate for those. So I hope you like this lecture, and before I end my lecture I would again request you to please like, share and subscribe to my YouTube channel, and also press the bell icon for any future notifications. I will be uploading several lectures on my YouTube channel so that you don't miss any lectures. So in these times of COVID-19 pending, I would just please stay safe, stay inside your homes, and good luck. Thank you.